For project number 2, our team decided to do question number 1, the pendulum problem, which is a simple pendulum and an elastic collision. So that means that energy is conserved, and we can also assume conservation of momentum. Another assumption we'll be making is gravity equals 10 meters per second squared. Equations that we will be using is conservation of momentum, which is m1 u1 plus m2 u2 equals m1 v1 plus m1 or m2 v2. And we'll also be using conservation of energy, which is potential energy equals kinetic energy. Kinetic energy equals 1/2 mass times v squared, and a potential energy for a pendulum is mass times gravity times length of the strings times 1 minus cosine theta. Or we'll also be using potential energy equals mass times gravity times height. For the equation, we are trying to find the height final of each ball. These balls are on a pendulum, and mass 1 is being dropped, and mass 2 has a initial velocity of 0. The variables we have are m1 equals mass of ball 1, m2 equals mass of ball 2, L equals the string lengths for both strings, theta equals angle, v1 equals velocity of ball 1 final after collision, and v2 equals velocity of ball 2 after collision. Kinetic energy is Ke, potential energy is Pe. U1 equals velocity of ball 1 before the collision, and U2 equals velocity of ball 2 before the collision. First, we'll find the velocity before the collision using conservation of energy. We know that the velocity of m2 before the collision is going to be 0 at it's at rest. However, we do need to find the velocity of m1 by using the kinetic energy equals potential energy. We will set 1/2 mv squared equal to mass times gravity times length of the string times 1 minus cosine theta. After we find the velocity, the initial velocity of mass 2, we will find the velocities after the collision using the conservation of momentum, which is m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. That being said, now that we have those variables, we can put it in the conservation of kinetic energy, and that is the kinetic energy initial equals kinetic energy of final, and these are the overall kinetic energies. We put the velocities in terms of known variables, and then we use post-collision velocities for the maximum height using conservation of energy, which is potential energy equals mass times gravity times height.
So the first step to solve the problem is, given the configuration, we want to find and represent the initial velocity of m1 before the collision. So by doing this, we can apply conservation of kinetic energy to say that the kinetic energy of the ball 1 at its initial velocity is equal to the potential energy of the ball at angle theta. So the way we set this up is we do, on the left side of the equation, the potential energy, which is the mass of m1 times gravity times the length of the pendulum times 1 minus cosine theta, which equals the kinetic energy at velocity u1. And then we write this in terms of velocity at u1 to get this equation here that represents the initial velocity of the first pendulum before the collision. And also note within the starting configuration that m2 will have a velocity of 0 because it is stationary. So now that we've determined what the initial velocity before the collision is for both balls, we want to find out what the velocity of the balls is after the collision. So to do that, because as we outlined earlier, the collision is elastic, that means we can use the conservation of momentum here. So M1U1, M2U2, M1V1, M2V2. If we substitute the like terms that we just found out here, we get this equation here. And then what we can do is, using some algebra, is rewrite this term in terms of V2. So we can represent V2 as a function of all these other constants here. After solving for representation of V1, we want to solve, V2, we want to create a representation for V1. So what we're going to do is, as we previously mentioned, because the collision is elastic, we can use the conservation of kinetic energy, which we have set up here. And we substitute the like terms that we found out previously. We found out the initial velocity before the collision for both of the balls. And then previously we just found the velocity for ball 1, V1, after the collision. So what we can do is we can substitute those terms in and also do some simplification of the equation. That gives us this equation here. And next, we can do some more algebraic simplification and group like terms and set it up such that we have a quadratic equation that has the variable set as V1. So V1 squared, and then V1 here, and then a constant here. And because this is a quadratic equation, what we can do is we can use the quadratic formula. And so we can substitute in the appropriate terms here to come up with this equation such that V1 is equal to this quadratic equation. And so when we do some more algebraic simplification and we actually begin to solve for V1, if we take this equation as it is and we add it, the result is square root of 2gl times 1 minus cosine theta. And as you may remember, this is what our initial velocity before the collision is. So this is not what we want to use to represent V1. Alternatively, if we subtract these terms, we get this equation here, which represents V1 in terms of the constants we already know, GL, theta, M1 and M2. And so that's how we find V1. So up here we have written everything we have known and solved for so far. V1 right here. And we also have V2 solved in terms of the constants we're given, but also in terms of V1. So what we want to do is we want to go back to the equation for V2, and we want to substitute the known V1 into the V1 in the equation. And so what that looks like when we substitute those known values is this equation here. And after some algebraic simplification, we get this equation for V2 here, which is represented in terms of the components we're given in the problem: M2, G, length, and etc. We now have V1 and V2 in terms of the constants given to us in the problem. So what we want to do right now after that is to find the height of each ball after the collision. So what we're going to do is, because like I said before, it's an elastic collision, we can use the conservation of energy and represent the height in terms of the kinetic energy is equal to the potential energy of the ball after the collision. So to explain further what that means, we set up the equation for ball 1 here. We have the kinetic energy side, 1/2 mass 1 times V1, which we just figured out here, squared, equals M1 times gravity times H1, which would be the height at which represents the potential energy of the ball at a height H1. And so what we want to do is we want to substitute in the terms we figured out here into the equation, and with simplifying it algebraically, we want to rewrite everything such that we have H1 here in terms of all the terms we know here. And so that leaves us with the height of ball 1 can be represented by this equation here. Through the same process, we can do the same thing for ball 2. Same deal, kinetic energy is potential energy. Set up the equation here, substitute in our like terms, and simplify such that we have h2, the height of ball 2, is this equation here.
One way that we can make sense of the equations that we have solved for the height of each of the balls is solving for units, and we want our units in meters, and this will these equations will give us meters because this would be kilograms over kilograms, which would cancel out, and then length is in meters, and so it would just be, you know, whatever this number ends up being, and then this is unitless, so we are given meters at the end of the problem. And then similar situation for the height of ball 2. This is unitless, this would be in meters, and these are both kilograms over kilograms, which would cancel out, leaving us meters, which is what we want. We can make sense of the equations that we solved for is if we change one of the variables in the equation. So for example, if we were to change the angle of when we released ball 1 to hit ball 2, this would create a lower height. And we know this because if we did the extremes, for example, if we did cosine of 90 degrees, cosine of 90 degrees is 0, and so 1 minus 0 is 1, and so this would, you know, create like the max possible height if we were to release it at 90 degrees, or vice versa if we were to do it at 0 degrees, so just like, you know, from the same position, this would create 1 minus 1, which is 0, and so there would be no height of ball 1 at all, and like same for here, like it would produce the same results, and yeah, so the greater the angle, the greater the max height of the ball can be reached, and if we decrease the angle, this turns into a smaller and smaller decimal point, which will ultimately lower the height of the ball, and this works for both equations. Another sense-making activity that we can do is creating values for the constant variables that we have in our problem, so that's going to be the mass, the angle, and the length. So for the mass of the two balls that we did, ball 1 20 kilograms and ball 2 10 kilograms, and so note that ball 1 is twice the mass of ball 2. The length of the rope or the string that the pendulum is on is going to be 15 meters, and then the angle at which the ball is released is 60 degrees. So we can plug that into our equations for each of the heights, and we get to the final height. So after plugging all of our values into the equations that we get 5 over 6 meters for height 1, or height 1 of the ball, and 20 over 6 meters for height of ball 2. And this makes sense because we know mass 1 is greater than mass 2, and it's actually twice the mass, and this makes sense because when we think about you know, the ball 1 hitting ball 2 and its mass is twice as great, it's going to be hitting it with a much greater force than if this was, you know, half and half. And then another thing that we can think about is, let's say these two balls were the exact same weight. And so if we put that into our equation for height 1 of the ball, so if these were both 10 kilograms, this would be 10 minus 10, which is 0, and would create height 1 of ball 1, 0, which makes sense because if these were the same weight, this would hit, and then this one would swing off, and this one would then like kind of replace this in this position, so the height would be 0. And you can think about like Newton's cradle and how that is true and how that would prove to be true with the equations that we solved for the heights and such.
So for the problem that is similar to the problem of the pendulum that we were analyzing, we decided it was activity 9-2. This activity was 2 bumper cars collide with each other and get tangled together. Car 1 with 100 kilograms moves north at 4 meters per second, and car 2 at 200 kilograms moves south at 3 meters per second. First, we had to find the final velocities of each car, and using the final velocities, we determine the initial and final kinetic energies of the car. With that being said, we found the initial and final kinetic energies were the same, and that means there is conservation of kinetic energy, which is also means that there is conservation of momentum. That is the same as our pendulum problem as well. First thing that is different is that the variables M1 and M2 for the cars were defined as 100 kilograms and 200 kilograms. And we also got velocities, so we were able to solve for the kinetic energies to find out that it was conservation of kinetic energy. However, our problem, it told us that it was an elastic collision, so we know that that means there is conservation of momentum and conservation of kinetic energy. Another difference is that using the velocity of our balls, the final velocity of each ball, we were trying to find a height, whereas for this equation, we were trying to find a completely different variable, which was kinetic energy, and just to see if it was an elastic or inelastic equation.